All right, in this ACT video, we are picking up where we left off, and this is Circles and Angles Part 2. In Circles and Angles Part 1, we talked about central angles, whose vertex is on the center of the circle, and inscribed angles, whose vertex is on the circle. So that was two scenarios. In this video, we're going to pick up two more scenarios. Like I mentioned in Part 1, it's important that you identify where the vertex is. So, our first scenario is when the vertex is inside the circle, not necessarily on the center, okay? It's just inside the circle somewhere. So it says that if the angle's vertex lies inside the circle, highlight that, then its measure is half the sum of the intercepted arcs. So let's look at the picture here. I've got a little formula for you, but our angle theta is right here. Now, it is intercepting arc AB, and then it is vertical to this angle here. So remember, vertical angles are congruent. So you could actually call that theta as well, and that's how we're getting the other intercepted arc to be arc CD. So what that says is the angle theta is equal to half the measure of arc AB plus the measure of arc CD. And that's when the vertex is inside the circle. The second scenario is the vertex is outside the circle. If the angle's vertex lies outside the circle, then its measure is half the difference of the intercepted arcs. So here, we have this angle, we're calling it angle theta, and its vertex is clearly outside of the circle, and we can see that it is intercepting this small arc AB and then this large arc CD. So the measure of angle theta is equal to the measure of arc CD, the bigger arc, minus the measure of arc AB, the smaller arc, divided by 2. And if you don't like the way I wrote that, you can also write it like we did in the last one. We can say theta is equal to half the measure of arc CD minus the measure of arc AB. It's the same thing. It's just two different ways to write it, so you just pick which one makes the most sense to you. Now, we have another scenario when the vertex could lie outside the circle. It's the same formula, if you will, but a different looking picture. So let's scroll down here. And now we also have this angle whose vertex is outside of the circle. So again, it's all about where's the vertex? On the center, on the circle, inside the circle, or outside the circle. Those are your four scenarios. So since it's outside the circle, we need to find the two intercepted arcs. We've got this small arc, BC, kind of hard to see there, a little bit much highlighter, but that's okay. I think you get the idea. And then we have this big arc, AC. Okay, and they share C in common, but that's no big deal. So you subtract those and divide by 2. Okay, let's look at an example. So here we want to find the value of each variable, and we've got two arcs. We've got this arc over here, which is 46 degrees, and we've got this arc over here, which is 90 degrees. And we need to find this angle X. So where's the vertex of the angle? The vertex of the angle is inside the circle. So that means X is equal to half the sum of those arcs, 90 plus 46. So the angle X is equal to half of 90 plus 46 is 136, and half of 136 is 68. So that angle is 68 degrees. Again, emphasizing that you need to look where the vertex is. Second example, you kind of probably know where this one's going, but it's not quite so straightforward. So here we're looking for X, the angle, and it's outside of the circle, and it has two intercepted arcs. The 30-degree arc, and this one that's 110. All right, now so since the angle is outside of the circle, then we could say that the angle x is equal to half the difference. Now, it does matter on the difference which one you subtract first. You need to do the larger number, 110, minus the smaller. Okay, it doesn't matter when you add, but subtraction, it matters. So x is equal to half of 110 minus 30, which is 80, and then half of 80 is 40. Again, vertex outside the circle. Now, this one's the one that's not quite so straightforward because we're not looking for an angle. We're actually looking for an arc this time, but we still have to use the same idea. In this case, we find the angle and we see that the vertex is outside of the circle. So when the vertex is outside of the circle, we know it's half the difference of the arcs. So the big arc minus the small arc. I don't have any names on here, so I couldn't name them, but you get the idea. So we're setting up more of an algebraic equation for this one. The angle, 70 degrees, is equal to half of the big arc. Now you have to look at the picture. X is going to have to be the bigger arc, which is half of x minus the smaller arc, which is 110. Then we would just multiply by 2. We can distribute the 1/2, but I kind of think it's easier just to go ahead and multiply both sides by 2. If you do that, those 2's cancel. And 2 times 70 is going to be 140 equals x minus 110. Add 110 to both sides. 110's cancel, and x is equal to 0, 5, 250. Now, we probably could have done this a little bit faster. So I'm going to ask you, did you see anything that we could have done this more efficiently? We hadn't talked about it a whole lot in this video, but the entire circle is 360 degrees. So if this piece from here to here is 110, we could have just said 360 minus 110, and that's 250. That's a much quicker way to do it, but I wanted to show you how we can use these theorems as well, in case it's not always so obvious. So always look to see where is the vertex. Is the vertex of the angle on the circle, making it a central angle? On the center, making it a central angle. On the circle, making it an inscribed angle. Inside the circle or outside the circle. You have 4 scenarios.